This is tutorial 5 of advanced power conversion and control. So last time we have talked about how the DC motors work and their characteristics. So today we will take a look at the torque and speed characteristics, right? So here we have like two more important equation, right? And the omega speed, that is equal to the terminal voltage divided by K into phi minus RA divided by K phi squared of K phi, right? Into the torque, right? Then omega we can write using the armature current like this. So these are two important equations. So using these two we can actually take a look at how the speed characteristics changes. So for a given torque, so that means when the torque is constant, the motor speed is a function of the following three quantities. So what are they? So as you can see, resistance of the armature circuit, right? So this is RA, right? Resistance of armature circuit, right? So what we can do is, so this is the default, the existing resistance, right? So for this one we can add a resistance to the armature circuit, so then it will change. So therefore we can change our omega, right? Then the second one is the terminal voltage of the armature voltage, which is this one, Vt. So you can see by reducing the armature voltage, voltage of the motor reduces the motor speed. So you can see omega and Vt, they are proportional. So when I reduce Vt, omega will reduce, right? So why we are only talking about the reducing the armature voltage? Because the DC motors, they are operated in rated voltages, right? So if we want to, even we want to, we cannot increase the speed as we want, right? Why? Because if we increase the speed, if we increase the voltage, that will not be able to withstand with the motor. So therefore we are talking about the reduction. Then the next one is the field flux. The next one is the field flux. Okay, so field flux means when we change the field voltage, right? When we feel the field voltage, what will happen is it will affect to this, and it will affect to this. So therefore, by reducing the field voltage, reduces the flux, and the motor speed will increase. So you can see when phi is reducing, when the field voltage is reducing, this phi value will also reduce, and therefore it will result speed increase. So from both of these two equations we can derive that. So but we need to note down these few things, right? So motors cannot operate with voltages higher than the rated values, right? So that is the fact, right? And therefore motor speed cannot be controlled by increasing the armature or field voltages beyond the rated value. So that's why we are talking about reducing the armature voltage and reducing the field voltage, right? Because we can reduce it, right? But of course there is a limit, but we cannot increase as we want, right? So therefore we had to consider those things as well. Then only voltage reduction can be implemented, hence the second method of speed control is only suitable for speed reduction, right? most of the cases. So this is this one it is suitable only for the only for speed reduction, right? And the next one, this method is suitable for speed increase, right? That means we are not going to expect to increase omega using this, and we are not expecting to decrease omega from this one. Why? Because when this field voltage or terminal means armature voltage, when they reduce, and omega will reduce, and here omega will increase. So therefore we are not going to increase omega using the second method. We are not going to decrease omega using the third method, right? So then we'll take a look at how to do the speed control by adding a resistance, right? So you can see this is the field, and this is the armature, right? So VT means the armature voltage, the terminal voltage of the armature, and this RA is the armature resistance, and here you have EA, the back EMF, and this is where we add the additional resistance. So we make it as a variable resistance, right? So from this one, right, from this one you can see that if we have drawn the torque speed characteristics, right? So we have studied these things in the lab class as well, right? So this is the torque, right, and this is the speed omega, right? So what is actually this value? This is the value when TD torque, that value equal to 0, right? When that value is equal to 0, so when TD is equal to 0, the omega value is the value in here, right? So as long as this, so that is this value, right? As long as this VT and the field voltage VF are not changed, so this will be a constant. So that's what it says in here as well, right? So as you can see it in, so that is the intercept, right? So actually this is in here you have minus, and what is this? This is actually the gradient, right? So the minus gradient will increase when we add a resistance, right? So that means we are moving when we increase, when we add a resistance, and when we increase in the R add value, what we will do is we will move from here to here by negative increase of the gradient, because here RA add, so squared minus, so this is the gradient, and this is the gradient. Here this is negative, right? So this is the gradient. So when we increase this R add, this will increase, right? It means when we increase R add, we will move in this way, right? So for a given torque, let's say at this point the torque is constant, let's say it is TD dash, right? So the torque value is TD dash at this point. So when that is the case, so can you see that for the can you see how this omega value changes, or the speed changes with the addition of the resistance? So you can see what will happen when we increase the resistance R add. What will happen to the omega? Omega will reduce like this, right? So actually at this point 4, at point 4, here you can see, right, at point 4, what is the value of omega? Omega is equal to 0, right? Omega value is equal to 0 at this point, operating point number 4, right? Like that we can understand. So even though we are adding the resistance for the intercept or the VT over K5, it will not affect, right? So the motor speed decreases as R add is increased. So note that the no load speed is unchanged, right? What is no load speed? If you ask to find, this is the no load speed, right? When there's no torque, that means that is our no load speed, right? So that will remain unchanged because we are keeping Vt and Vf constant. Okay, so consider this example, right? You may have done this one also, right? A 150 volts DC shunt motor drives a constant torque torque load at a speed of 1200 rpm. The armature and field resistance are 1 ohm, so Rf equal 1 ohm and Ra equal 150 ohms. The motor draws a line current of 10 amperes, right? So then calculate the resistance that should be added to the armature circuit to reduce the speed by 50%, right? So the speed should be decreased by 50%, right? So therefore by using this one, we will assume this is so at this space we have only the armature resistance. The resultant armature resistance is Ra. That means we haven't added anything, let's say plus 0. Then we will assume this is the case when this is added. So therefore at that time, let's mark so as I have marked here, it is omega 2, right? Omega 2, right? Omega 2 value, right? All right. So according to the above figure, so we have done that. Since the motor is a shunt machine, the line current is equal to the armature current plus the field current, right? So okay, so this so our motor is a shunt, right? So shunt means the line current comes, right? Then it will divide into armature current and the field current. So let's mark the armature current as IA1, right? And here we were given Vf is equal 150 and Rf is equal ohms, right? So therefore what is If? If is 150 divided by 150, which is equal to 1 ampere, right? So therefore here this is given as 10 amps and this is 1 amp. So therefore Ia1 is 9 amps, right? So we have found that. And then we know that EA1, what is this EA1? That is the back EMF, which is equal to K5 omega 1, right? And which is equal to V minus IA1 into RA, right? So what is this voltage? Voltage is the terminal voltage because this is a shunt, right? Because this is a shunt one, so here you will have the armature part and here you will have the field part. So therefore this voltage is 150 volts, right? So we can write so in the previous case we don't have a resistance added, but in next case we have a resistance added. So therefore we can write these two equations. So if I mark this one and this one as 2, 1 divided by 2, it is equal to EA1 divided by EA2, which is equal to omega 1 divided by omega 2, which is equal N1 over N2, right? So this is the speed in RPM, right? So omega 1 and N1, they are proportional, so we can divide it like this, right? So then after we divide here omega 1 is 1200, right? 1200, and omega 2 it is actually 600, which is 0.5 into 1200, and it is equal to 150 minus, here this is equal to 9, right? For the both cases, this is equal to 9, right? Only this is added, or add is the one that you add in, right? So therefore if you solve this, you will get if you add 7.83 ohms, right? So but note down the armature resistance is 1 ohm, right? So we are adding more than like 7 times of a resistor at the armature in order to do this speed reduction, right? So when we add that resistance, or add, the speed will reduced by 50%, right? So the next one, assume the rotational losses to be 100 watts. Calculate the efficiency of the motor with and without the added resistors, right? Okay, so first of all we have to calculate the input power, right? Input power is equal to, since this is DC, what we are getting is 150 into the line current, right? 150 into 10, which is 1500, right? Then losses we can write as field loss, armature loss, and the rotational loss, right? So then so therefore yeah, we can calculate in here what is IF. IF is 1, right? So 1 squared into what is RF, it is 150 plus, right? What is IA? It is unchanged, so 9 squared into RA, it is 1, right? Plus the rotational losses, right? So which is equal to this 331 watts, right? So then this is actually the P out. P out is equal to P in minus P losses, right? So this is P in. So if you calculate, you will get 77.93 efficiency, right? So but what will happen when we add the resistance, right? So this will so the field losses, that will be same. Then armature losses, it will be 1 plus 7.83. Why? That resistance is added, and the rotation losses is still, it is 100, and if you calculate that, you will get this much of losses, 965.23 losses, right? So then if we calculate the P out, which is input minus losses, right? It is P out, and here divide by 1,500, which is P in. You will see now the efficiency, it has reduced to this much of a value. So previous it is about 78 something, now it is 35 or 36 something, right? 35 something, right? So that's the thing. The losses, the additional losses that has added because of the added resistance, it is this much, right? 330. So this much of right? Can you see? So previously the losses are 331, now the losses are 965.23, right? So therefore there are high losses that is that has applied in here, right? So therefore when we add the resistance, it is not that much efficient. Okay, so then next one, calculate the resistance that must be added to the armature circuit to operate the motor at the hold in condition, right? So if we consider this is our so no R add, right? So this is the position where the motor holds means omega is equal to 0. Yeah, at this is 0, so therefore omega is equal to 0, at this point. So that is the operating point in here, right? So therefore let's say it is r add 3 that we have to add in order to get that. Right. Okay, so what we can do is we can equate omega equals 0, right? If you make it omega equals 0, you can see k phi omega, it is equal to v minus ia ra plus r rad. Let's say this is r rad 3, right? So therefore r rad, it is equal to v over ia minus, okay, so v over ia minus ra. So this is actually the terminal voltage, which is equal to 150. Then IA, the armature current is 9 minus armature resistance 1, so 15.67 ohms. So if you add, so actually this is 3, because at that version we have written it as R at 3. So therefore if we add 15.67 ohms resistance, what will happen is our motor will not move, it will stop, right? It will stop. So okay, that means it will make our motor into this position, right? So like that we can calculate, if we add up to this much of resistance except the RA, our motor will hold.